We are in lessons 4.03 and 4.04 today. So that's what we should have. You should have had 101, 401 and 402 last week. I will hang around after we do this lesson and do as many as the discussion-based assessments as we can get done. For those of you who have not finished that, I do not expect I will have much availability this week unless I do it in the hospital. I'm going to be in the hospital starting tomorrow. For 5 days of chemotherapy because some test results came back and they said, whoa, things are bad. And I'm like, I've been telling you things are bad. You guys just not paying attention. But they finally got some tests back where they saw things were bad. So I'm going to have 5 days of chemotherapy starting tomorrow. So we're going to do discussion-based assessment. And then I don't know how I'm going to feel in the hospital. Chemotherapy can make you pretty sick sometimes. But if I'm feeling pretty good, I may open it up, send some emails out, and do some discussion-based from my hospital bed. Could do that. We'll just wait and see. But I'm not going to count on that because I know how bad that can make me feel. So, all right, let me put up my camera and let's talk about these lessons we have this week. Okay, so this week with the properties of logarithmic functions. So I already worked a little bit with logs in the last lesson here, but let's talk about logarithms. So if we have, and let me just mention that when you have in your calculators, most of your calculators, if it has even the cheap calculators, even the $5 calculators, we usually have a logarithm button. So you can put in log 100 in there and hit enter, and it's going to give you a 2 as an answer. Because even the little cheap calculators have logarithm, but it automatically uses base 10. Which is what our number system is based off of, base 10. So log is automatically base 10 unless you have a calculator that lets you enter it as something separately, right? So basically this is saying when you have a logarithm, that's saying 10 to this power equals this. 10 squared equals 100. So when you have a log 10 of 100, that's saying 10 to what power equals 100, and the answer is 2. 10 to this power equals 100. So that's how a logarithm is basically set up. Today we're going to talk about if I have log, we just put an example here, log base 8 of 6. 8 to what power equals 6? Like, well, that's less than 1. Yeah, it's going to be some decimal number. And if you just have a cheap calculator, that's not going to help you because it wants to do everything in base 10, right? So you got to get one of the little fancier calculators. Or no, actually you don't. You can do this with a cheap calculator because we can calculate this the same way. Log 8 6 is the same as log 6 base 10 over log 8 base 10. If you take with your little cheap calculator and say log of 6 divided by log of 8, that'll be the same thing as the log base 8 of 6. Let's calculate that while we're here. I just kind of made those up, so I don't have an answer for it. So let's see. This one has the capability of doing other logs, but I'm just going to do log. I'm going to tell it base 10 because it asked me the base in my calculator. Don't say that the base 10 of 6 divided by log, and again, I'm telling the base 10 of 8. So what is log 6 of base 8? It is 0.861. Let's round it to 4 decimals, 8617. Now, since this calculator has the capability of doing it the other way, let's just check that. Log base 8 of 6. So I can tell it log base 8 of 6. Look at the exact same answer, 0.8617. So this is a nice shortcut. So any cheap little calculator can help you figure out what is log 8 of 6 by just converting it. This is the change of base formula. Change of base formula. And it basically says the generic form would be when you have log b of y. Geez, looking funny today. It's the same thing as log y divided by log b. Okay, so that's the change of base formula. Very useful so that you can use any calculator to figure out a logarithm answer on that. Let's see. Let's talk about the equality property of logs. Basically, that says if we have log 4 of x, which we don't know what that is necessarily because x could be any number, right? It's a variable, equals log 4 of y, then, oh, I guess I should write that differently. Then x has to equal y. Because log 4 of x, if it equals to log 4 of y, they have to have the same answer. They have to be equal to, x has to be equal to y. That one's kind of what we can kind of call that the duh property, right? But that's important to have that in your notes and just to remember that log 4 of x equals log 4 of y, then that just means x has to equal y. So logarithms aren't some weird funky thing that work outside of the rules of math. That's pretty simple. If everything's the same except x and y, and these are supposed to be equal to each other, then x has to be y. These both have to be a 7. These both have to be 16. They both have to be something for those to be equal to one another. So let's look at the next thing, the product property. It's great to have all these in your notes. Remember, you can use your notes on any tests or assignments or anything. So if you have these properties written down, they can save you a lot of heartache trying to remember these things. So the product property says when two or more logarithmic expressions with the same base, right, whether it's base 4, base b, base 10, base 8, whatever they are, when they are added, you can just multiply their arguments. So let's say let's do log 7 of 3. If we have log 7 of 3 and we're adding to that log 7 of 5, right? So these are both log 7, and we're adding them together, whatever they are. That is going to equal log 7 of 3 times 5, which will equal log 7 of 15. So that's what the product property says. If I'm having these two logs with the same base, whatever their arguments are, instead of having to calculate those separately and add them together, we can just multiply the arguments and say, well, this is the same as log 7 of 15 because 3 times 5 is 15. So that is our product property. And of course, if we need to figure out what this is, then we have a cheap calculator, we can put it in as this, log of 15 divided by log of 7, and we can have an actual answer for that. So that is the product property. Now let's talk about if we have a product, we can have a quotient, right? Product is when you multiply, quotient is when you divide. So let's look at the quotient property of logarithms. All right, so then it says if we have, again, two that are the same base, say log 7. So if I have log 7 of 54, right, and I'm subtracting from it log 7 of 9, and that's the same thing as log 7 of 54 divided by 9, or log 7 of 6. So notice when we add, then we multiply. If these are subtracting, then we divide. So if we're adding two logs that have the same base, we can multiply the arguments. When we're subtracting two logarithms that have the same base, we can divide the arguments. So 54 divided by 9 is the 6. So it's log base 7 of 6. It's the same thing as doing this equation right there. So wonderful. More properties to add. Let's see what else we have. The power property. Absolutely. We need to know the power property. The power property. The power property of logarithm tells us that if we have 4 times log 7 of 3, all right, so we got log base 7 of 3, the argument's 3, and we're multiplying it 4 times, we can rewrite that using the power property to say that's the same thing as log 7 of 3 to the 4th power. So this 4 comes around and becomes an exponent. 3 to the 4th. So then this is the same as log base 7. 3 to the 4th is 3 times 3 times 3 times 3, or 81. So 4 log 7 of 3 is the same as log 7 of 81, because the power property says we can make that number up front and an exponent. Now remember, we can do this the other direction too. If we're trying to solve something and we have an exponent, we can just bring it up front, and that's the same thing as 4 times that. So let's see. And if we solve one, look in that. Log equations, last thing I'm putting on this page, I'm running out of paper. Log equations with constants. So to solve a logarithm equation using constants, here's what we need to do. Let's say we have log 7 of x, and it equals 3. Right? Well, we know if the way a logarithm works is this is saying 7 to the 3rd equals x. See, logarithms and exponents are inverse operations of each other. So all we have to do is solve 7 to the 3rd power. So 7 times 7 times 7 is 343. So that's what x equals. So that means we were asking basically log 7 of 343 is equal to 3. Because you're asking 7 to the 3rd power equals what? And it's 343. So when we just have that one variable there and we have the 7 and the 3, we can actually solve that and come up with a nice solid answer there. So that is the basic summary for lesson 4.3. It basically lays out all of these properties, and it gives you practice problems to make sure you understand them. It'll say, okay, try this, and it'll give you this and have you type in what is it equivalent to. So you'll have to type the 15 in there. Different things along the line. So this is a great, it's got 10 pages, but 5 of those are just practice pages where it'll give you a problem and say, okay, what's this? What do you type here? What do you type here? What do I type here? And that just helps you. Do you understand what you're talking about? Even if you have these written down, do you understand how to use them? That's when you go through those practice problems on there and look at the first page of the practice problems. Practice. Evaluate each expression to the nearest hundredth. So it has log 4 of 8. So one of our first practice problems is taking log 4 of 8, and you have to answer that to the nearest 100th. Well, that means you need to take your calculator and you say, okay, well, I'm going to put in log 8 divided by log 4 in my calculator, even if it's a cheap calculator. And what answer does that give you to the nearest 100th? And they've got a multiple choice in there. So that just gives you some practice, some opportunity to try what we're learning here and what we're seeing. So that is 4.03. Let's look at 4.04. It doesn't have as many pages as this doesn't have all of these different properties it's teaching. And now we're using some of them in this one. And this one we're talking about the compound interest stuff, which we could hit on in lesson 2 last week. It's talking about using logarithms with different bases. Let me go to our summary page here and work off of our lesson summary for this. Okay, so the lesson summary for this talks about Solving an exponential equation on unequal basis. Rewrite the exponential equation as a log, solve for the variable, and check your work. So let me pull up one of the practice problems for us to use that and go with. All right. So here's one of our practice problems. So if we have 5x equals 20, all right, 5 to what power equals 20? Oh, we're like, well, 5 to the first power is 5. 5 squared is 25. Oh, it's somewhere between 1 and 2, but we don't know the exact answer on that. So what we have to do when we have like this is we'll just set the logarithm of both sides, since this is an exponent. So we would say, okay, well, log of 5 to the x power equals log 20. We can just take the logarithm of both sides to help solve this. Now we have our power property. Remember we talked about with an exponent? We can move that out front. So this is the same as x times log 5 equals log 20. Now we have something we can work with. We can put in our calculator on this base 10. What is log of 5? So we'll hit our log button. Log of 5 is the same as, so x times, let's go 5 decimals, just not round too early. So 69897 is what log 5 is. And then over here, log 20 I'll just type in 20, and that is equal to 1.300103, going 5 decimals again. And 5 decimals is pretty extreme. I mean, you might cut off at 3 decimals to be fine. So now we've got a simple coefficient x equals that. So divide both sides by 0.69897. 69897. 97. There we go. And that will give us what x equals. So 1.30103 divided by 0.69897. So that equals 1.861. I want 5 decimals. I'll go decimals again. 1.86. What about 1.86 if we can? So then you need to check your work. All right. So if we said check our work, we go back to the original equation. So we're saying, okay, 5 to the 1.86 power equals 20. Is that right? Well, let's go back and take a power to a power on this. Let's see on my calculator how to do that. All right, now I've got to refresh myself on all these special functions on there. Oh, there's 5 raised. Oh, I didn't want 2 5s. 5 to the power of, have this little power of button right in there. 1.86 and equals 19.95649. So it would round to a 20. So that is really close. If I include another decimal, 5 to the 1.861. Oh, I did something wrong. I got an extra something there. 1.861. Now I'm at 19.988. See, the more decimals I include, the closer I'm going to be to exactly to that 20. 5 to the 1.86135. So now I'm at 19.99989. So the more decimals I include, the more accurate my answer gets to be, and closer to 20. So that is our correct answer on how to do that, on solving those. Let's see what other examples they have us work here. Oh, they do a little bit with the decay issue. Let's see, what is their, I want to use their same formula for growth and decay. Growth and decay is one that is used in like bank accounts and all kinds of good stuff like that. So they use a time, the amount for time is equal to the P is like your starting principal, the starting amount you have, whatever it is. 1 plus R. R is your rate. right? The rate of interest that you're getting in your savings account, or the rate of interest you're paying on your loan, or whatever it is, and T is the time. So you can modify this for the road of growth or decay. So when you have this 1 plus R, if R is greater than 0, right, that means you're adding to 1 and you're multiplying times the principal. This means this is growing. That's growing. If R is bigger than 1. If R is less than, if it's bigger than 0, less than 0, then it's decaying. All right, it's going down because you're subtracting. I'm sorry. R is greater than 0. I actually have those reversed because with this plus, if we're adding, no, that's right. If it's less than 0, if it's a plus, we'd be subtracting if it's less than 0. So if R equaled negative 0.05, then that means 1 plus a negative, this would be a 0.95 then, which means it's going down, right? Because it's less than 0. So if it ended up going down 0.95, that means after each time period, you've only got 95% of what you started with. In the next time period, you only have 95% of that and 95% of that. So it's going down 0.05, or the same thing as 5%, right? Remember, 2 decimals, 5% is the same thing as 0.05. That's how you can tell it's decaying. Where if this was a positive 0.05, then it would be growing. You'd be at 1.05. So every time period, you'd be adding 5% to how much you had. Adding 5%. So being able to do that growth and decay in different problems is very useful, because a lot of money kind of stuff goes with that. But also in different experiments and different things, they talk about isotope, and isotope decays at a rate of 40% every decade. That's one of the examples there. Find the adjusted rate of decay if it's going to be calculated annually. So they have the principal amount, what it would start at, would be the P. So they say you take the A for the time period and be whatever the principal is, right, times the 1 plus R times the time period. So for what we have, if we have this isotope that decays at 40%, then our amount would be whatever it starts with, and they didn't give us a starting. But if it's going to decay, it'd be 1 minus 0.4 T. So it means 40% every time period. 40%. So if adjustments for taking measurements every year instead of every 10 years, because this is 40% per decade is what they told us, 40% per decade. So if we need to adjust that, it's like, okay, well then instead of this being P, because 1 minus 0.4 is 0.60, we'd have to adjust that. If we're going to do it every year instead of 10 years, we're going to say 1/10 of that. 1/10 of that for every 10 T's, because instead of years, it's 10 years is what they're looking at. So 1/10 of that for what it is every 10 years. So if you have a starting amount, you can plug that in and pull those numbers out of there. So your rate of decay would be changed on there. Let's see. Yeah, they don't have a whole lot of examples on this one because we don't have nearly as much in lesson 4.04. It's just dealing with a little bit more of being able to solve things like this, or working more with the growth and decay with your principal and your rate and all of that with your time periods. So work on these practice problems, work on the problems that use these properties. These are very important to understand logarithms. Logarithms are very useful. We have to have something that kind of counters exponential. So if you have something in an exponential, we can use logs as the inverse operation and vice versa. So if you had trouble in lessons 1 and 2 with any of that, you can email me. We can get together personally together on that, just one-on-one, and kind of help you with that. But this should be a follow-up for the lessons you did last week. So you should already have some understanding of the logarithms come into this. So that's all I'm going to present for this week's lessons. If you have not done the discussion-based assessment for last unit, hang around. I'll be happy to get those going today and try to get those out of the way for you before I end up in the hospital the rest of the week. and I won't be here to do that. I don't want you to have to wait till after Thanksgiving when you've totally forgotten everything. So that's why I want to try to get those done today. And also want to try to see if I can do it later in this week. Again, I can't guarantee that. Don't know how I'm going to feel the rest of the week. So if you have your discussion-based assessment done, if you don't have any questions, then you are free to go. And we will not be having class anymore this week since I will not be here. So have a great day.
Let's get out of here. Word to your multiples. Math, baby.